This is Adel Gastli. I'm going to present to you part 2 of the chapter about three-phase induction machines, or what is called also asynchronous machines. In this part, I will present the principle of operation of induction motors. When a live conductor with a current I is placed in a magnetic field B, it is influenced by Lorentz force, which tries to move it through the magnetic field. The direction of this force is determined by Fleming's left-hand rule, where the second finger points to the current direction, the forefront finger points to the magnetic field, and the thumb points to the direction of the force. This magnetic field is placed in the stationary part, which is the stator, and is crossing the rotating part, which is the rotor, through an air gap between the stator and the rotor. The conductors, influenced by the electromagnetic forces, are located in the rotating part. A three-phase voltage is usually applied to the three-phase stator windings. Note that the three-phase voltages are time-shifted with 120 degrees in three-phase system, and the three-phase stator windings are shifted from each other in space by 120 degrees. This combination of time and space shifts, 120 degrees each, creates a rotating magnetic field inside the stator that rotates at speed called the synchronous speed. Now, since the conductors of the rotor are placed in a rotating magnetic field, according to Faraday's law, an induced voltage is generated inside the rotor windings. And since the rotor windings constitute a closed circuit, a rotor current flows in these windings. Now, according to Lorentz's law, the interaction between the induced rotor current in each winding conductor and the stator magnetic field that is revolving generates a force on the surface of the rotor. These forces create a torque on the rotor surface, which makes the rotor rotate and try to catch up with the stator magnetic field. As soon as the speed of the motor equals that of the stator magnetic field, there will be no flux cutting by the rotor conductor, and thus the rotor current becomes zero. Thus, there will be no torque, and the rotor will tend to slow down, and the mismatch between the rotor speed and stator magnetic field, that is called slip, will make the rotor conductors cut again the magnetic field lines, and thus induce a rotor current and a torque again. So the rotor will never be able to rotate at exactly the synchronous speed because of mechanical torque due to bearing and air friction, which the motor needs to compensate for with the generation of its own torque. Note that at steady state, the load torque and the motor-generated torque must be equal so that the speed settles at a certain value. Otherwise, the speed will be increasing or decreasing depending on the difference of these two torques. Next, we'll see more in details how the rotating magnetic field is produced inside the stator. To explain why and how this magnetic field rotates, we will consider step by step what happens inside the stator of the machine. Let us consider only one phase winding. A magnetic field is induced when one of the phase windings is connected to one of the phase of the supply voltage. This magnetic field has a fixed location on the stator core, but its magnitude is varying sinusoidally in time and pulsating in space between north and south. The pulsation speed of the magnetic field is determined by the frequency of the AC line. For instance, 50 Hz case, the field changes direction 50 times per second. Now, two magnetic fields are produced in the stator core when two phase windings are connected. In a two-pole case, there is a 120 degrees displacement between the two fields. There is also a time interval between the maximum values of the two fields. That is why and how a magnetic field is created which rotates in the stator. However, this field is asymmetrical until the third phase is connected. When the third phase has been connected, there are three magnetic fields in the stator core, and there is 120 degrees displacement between the three phases. The magnetic fields of the individual phase windings make up a symmetrically rotating magnetic field called the rotating or revolving magnetic field of the motor. For instance, let us consider the situation at point P1. At this point, the flux at phase 1 is at its maximum value, while the fluxes at phase 2 and 3 are at half maximum value. Thus, the resultant flux is the sum of the three instantaneous vectors that are displaced 120 degrees, and the resultant vector is on the horizontal axis with an amplitude equal to 1.5 times the maximum flux. Now, if we move to point 2, the flux at phases 1 and 3 are equal to square root 3 over 2 phi max, while the flux of phase 2 is 0. So the resultant flux vector has the same amplitude, 1.5 phi max, but has rotated anti-clockwise and positioned at an angle of 30 degrees. Now, if we move to point 3, the fluxes at phases 1 and 2 are equal to 0.5 phi max, while the flux at phase 3 is equal to phi max. Therefore, the resultant flux vector has the same amplitude but has rotated further anti-clockwise and positioned itself at an angle of 60 degrees. Notice that the amplitude of the resulting field is constant and equals to 1.5 the amplitude of the alternating fields. It rotates at a speed of ns equal the frequency multiplied by 120 divided by the number of poles p. When the magnetic field vector rotates one revolution and is back to its starting point, the vector tip will have traced a complete circle. This speed is dependent on the number of poles P and the frequency of the supply voltage F. So the stator flux makes one revolution between two stator poles in t seconds, which means that the speed of rotation of the stator flux between two poles is F revolution per second, where F is the frequency of the power supply voltage. Thus, for a machine with P over 2 pairs of poles, the speed of rotation of the stator magnetic flux is F over P over 2 revolution per second, which is equivalent to 120 F over P revolution per minute, RPM. Let us summarize again the principle of producing a rotating magnetic field in an induction machine. When three-phase balanced sinusoidal voltages are applied to three-phase balanced windings, displaced from each other by 120 degrees in space, then a rotating magnetic field is produced, as we have seen in the previous slides. The speed of rotation of this magnetic field is called synchronous speed and is determined as ns for synchronous speed is equal to 100 times the frequency of the power supply voltage divided by the number of poles in the machine. This synchronous speed can also be represented by its equivalent angular synchronous velocity expressed in radian per second and define it as omega s is equal 4 pi f divided by p. So as you can notice, the synchronous speed depends on the number of poles and the supply frequency only. Since we have only frequencies of 50 Hz and 60 Hz and discrete even number of poles, we'll have discrete values of the synchronous speed. For instance, if we have a two-poles machine and 60 Hz power supply, then the synchronous speed will be 3,600 RPM. While for 50 Hz power supply, the synchronous speed is 3,000 RPM. Now, if the number of poles is 4 instead of 2, for 60 Hz, the synchronous speed will be 1,800 800 RPM. And for 50 Hertz, the synchronous speed will be 1500 RPM. This table presents all possible synchronous speeds for both 60 and 50 Hertz frequencies and for several number of poles up to 12. Note that the number of poles should be always an even number because it is not possible to have a north pole without a south pole. So we always have dipoles. Now, let us look at the principle of operation of the induction motor. We'll consider a square cage rotor type machine, but the same principle applies also to the wound rotor type machines. If we consider the rotor cage that is made of several rods that are placed inside the rotating field of the stator, then a rotor rod placed in the rotating field is passed or crossed, or also we say cut by magnetic poles. Therefore, because the field is rotating at different speed from the rotor rod, it will cut the rotor rods at certain frequencies. For instance, at standstill, when the rotor is not rotating, this frequency of cutting the rods is the same as the supply frequency. Now, we know that according to Faraday's law, the changing magnetic flux seen from the rods of each poles induces a back EMF and hence a current in the rotor rod because the rotor circuit is closed. The interaction between flux and the induced current in the rod creates a force which direction can be determined by the left-hand rule. So each rod of the cage will have a force exerted on it because of the interaction between the stator magnetic flux and the induced current inside the rotor circuit. So the rods of the rotor cage are influenced, each one by a force F. The direction of this force is determined by the direction of the field and its rotation. So when the field is rotating, the next pole passing the rotor rod is of opposite polarity. Therefore, it introduces a current in the opposite direction of the first one. However, as the direction of the magnetic field has also changed, the force is still affecting the rod in the same direction. So if the whole rotor is placed in the rotating magnetic field, all the rotor rods are thus influenced by forces making the rotor rotate in the certain direction. Notice that the rotor speed will not reach the speed of the rotational field as no current are induced in the rotor rods when the speeds are the same. In other words, if the rotor speed equals the stator field speed, then there will be no induced rotor current and hence no force or torque. In this case, the machine will slow down because of the load or rotational loss torque. So the rotor speed will be always less than the synchronous speed. For the induction motor, the rotor current is produced by induction principle, and that is why this type of machine is called induction machine. On the other hand, since the speed of the rotor is different from the synchronous speed, this type of machine is also called asynchronous machine. Let us make a short comparison between the DC motor that we studied in the previous chapter and the induction motor. In DC motors, an electric current is supplied externally to the rotating armature through brushes and commutator. The interaction between this current and the magnetic field that is produced by the field winding on the stator produces a torque which rotates the motor armature coils. In contrast, induction motors use shorted wire loops on a rotating armature and obtain their torque from currents induced in these loops by the changing magnetic field produced in the stator or stationary coils. Going back to the difference between the rotor speed and the synchronous speed, the rotor will eventually reach a steady state speed n that is less than the synchronous speed ns. The difference between the two will be called the slip and is defined as shown in this equation. So the slip is a ratio without a unit that is actually calculated as the difference between the synchronous speed and the rotor speed over the synchronous speed. It can be expressed also as a function of the RPM speeds or the radian per second velocities as presented here. So here ns is the synchronous speed, n is the rotor or motor speed, while omega s is the synchronous velocity and omega is the rotor velocity or motor velocity. Note that the velocity and the speed have a relationship between them as shown in these equations. Now let us look at the induced back EMF. The instantaneous value of the induced voltage in n turns coil is given by this equation, which is E1 is equal minus N1 d phi by dt. Considering a sinusoidal expression of the flux, phi is equal phi m sine omega t, where phi m is the maximum flux and omega is equal to pi f. F is the frequency of the voltage, supply voltage. Then we can write E1 is equal minus N1 omega phi m cosine omega t, which is derivative of the flux, which also equals N1 omega phi m sine omega t minus pi over 2. So you can see that the flux and the voltage are in quadrature phase shift between them. Now the RMS value of the induced voltage or back EMF is obtained as 4.44 F N1 phi p, where phi p is the flux per pole. Since there are two fluxes, the stator flux and the rotor flux, we'll have also two induced voltages or back EMF, E1 induced in the stator and E2 induced in the rotor. Before finishing this part, let us summarize some important definitions. We designate by N the rotor speed or the motor speed with regard to the stator. And S will designate the speed of the stator field with regards to the stator, or what we call the synchronous speed also. And R will designate the speed of the rotor field with regards to the rotor. S will designate the slip, F the frequency of the induced voltage in the stator or supply frequency, and FR the rotor circuit frequency or the slip frequency. Now, the speed of the rotor field with respect to the rotor is designated by NR and equals the difference between the synchronous speed and the rotor speed, and is equal to S multiplied by NS. So it means the slip multiplies by the synchronous speed, and is called also the slip RPM. Now, if you consider that the frequency of the rotor circuit, which is called slip frequency, FR, we can express the slip RPM similarly to the synchronous speed equation as NR is equal to 120 multiplied by FR divided by pi. We can then deduce FR as P multiplied by NR divided by 120, or P SNS divided by 120. Now, considering the equation of the synchronous speed as a function of the stator frequency and poles, we can write the slip of the rotor frequency equal to S multiplied by the stator frequency. It should be noted that both the stator field and rotor field rotate always at the same speed with regards to the stator. And this speed is called the synchronous speed, while the speed of the fields with regards to the rotor is the slip speed nr, which is also equal to s and s. Now, I would like to invite you to watch this animation from YouTube, which explains very well the principle of rotating magnetic field in the induction machine that we have just seen through the previous slides, and explains also the principle of operation of the machine. You can find the link below in the description also.
Induction motors are the most commonly used electrical machines. They are cheaper, rugged, and easier to maintain compared to other alternatives. In this video, we will learn the working of a three-phase squirrel cage induction motor. It has two main parts: stator and rotor. Stator is a stationary part, and rotor is the rotating part. Stator is made by stacking thin-slotted, highly permeable steel laminations inside a steel or cast iron frame. Winding passes through slots of stator. When a three-phase AC current passes through it, something very interesting happens. It produces a rotating magnetic field. To understand this phenomenon much better, consider a simplified three-phase winding with just 3 coils. A wire carrying current produces magnetic field around it. Now, for this special arrangement, magnetic field produced by three-phase AC current will be as shown at a particular instant. With variation in AC current, magnetic field takes a different orientation as shown. From these 3 positions, it's clear that it's like a magnetic field of uniform strength rotating. The speed of rotation of a magnetic field is known as synchronous speed. Assume you're putting a closed conductor inside it. Since the magnetic field is fluctuating, an EMF will be induced in the loop according to Faraday's law. The EMF will produce a current through the loop. So, the situation has become like a current-carrying loop is situated in a magnetic field. This will produce magnetic force in loop, according to Lorentz law. So, the loop will start rotating. A similar phenomenon happens inside an induction motor also. Here, instead of a simple loop, something very similar to a squirrel cage is used. Three-phase AC current passing through stator winding produces a rotating magnetic field. So, as in the previous case, current will be induced in bars of squirrel cage, which is shortened by end rings, and will start rotating. That's why it's called an induction motor. Electricity is inducted in the rotor by magnetic induction rather than direct electric connection. To aid such electromagnetic induction, insulated iron core lamina are packed inside the rotor. Such small slices of iron make sure that eddy current losses are minimum. This is another big advantage of a three-phase induction motor. It is inherently self-starting. So, you can see here that both magnetic field and rotor are rotating. But, at what speed will the rotor rotate? To obtain this answer, let's consider different cases. Consider a case where the rotor speed is the same as the magnetic field speed. Since both are rotating at the same speed, the rotating loop will always experience constant magnetic field. So, there won't be any induced EMF and current. This means zero force on rotor bars. So, the rotors will gradually slow down. But as it slows down, rotor loops will experience a varying magnetic field. So, induced current and force will rise again. And the rotor will speed up. In short, the rotor will never be able to catch up with the speed of the magnetic field. It rotates at a specific speed, which is slightly less than synchronous speed. The difference between synchronous and rotor speed is known as slip. Rotational mechanical power is transferred through a power shaft. In short, in an induction motor, electrical energy is entered via stator and output from motor. Mechanical rotation is received from rotor. Energy loss during motor operation is dissipated as heat. So, a fan at the other end helps in cooling down the motor. Hope you got a good introduction on the working of induction motors. Thank you.
This is the end of this part. Thank you for watching this video.